volume from cross-sections. What we cover in this video is sometimes referred to as the slicing method. And before we jump in to how this method works, we are going to review the geometric interpretation of our integral. So if we have some function f that ranges along some interval from a to b, we've learned that the geometric interpretation is the area between that function curve and the x-axis. And how we calculated that area initially was by introducing approximation methods, whether it be our RRAM, LRAM, MRAM, or trapezoid method. But those first three methods utilized rectangles. And we use rectangles of equal width but varying heights. And the act of adding these rectangle areas together gave us an approximation for that area that we were looking for. And then we said, as we introduced more and more rectangles with smaller and smaller base lengths, we were able to get a more accurate depiction or representation for that area. And that is where the integral came into play. We said as the limit of the number of rectangles we use approaches infinity, or as delta x, that base length, approaches 0, we would get the exact area under the curve. And the structure of that integral, remember that elongated s we can think of as a sum ranging from a to b, the endpoints of the interval in which we're trying to calculate the area between. And we had something that looks like f of x dx, where we learned f of x represents the height of any rectangle at some point within the interval from a to b. And we can see on our picture that the distance from the x-axis to the function curve is in fact f of x. So that represented our height. And we also learned that that dx could be thought of as the difference between x values, or our delta x, which is ultimately our base length. So here's our height, and here's our base. And knowing that the area of a rectangle is calculated by doing base times height, we can view this integral formula as, in brackets here, the area of a rectangle added up along the interval from a to b to get the exact area under the curve. Now, how does this relate to volume? Well, is there a methodology that could be used of the same principle and carry it over to something that's 3D? So instead of rectangles approximating 2D area, what could we use to approximate 3D volume? Well, if we're going to try to use the same method, how about we implement prisms? Okay? And that is exactly what we're going to do. So to illustrate how that looks, I'm going to jump over to an example of a sphere that is divided into cylinders. So on this picture, you can see we have this sphere, and it is composed of a bunch of cylinders. So we can think of that cylinder as kind of the special type of prism. And if we could add together the volumes of all these prisms, we would be able to calculate an approximation for the volume of the sphere as a whole. Now, how do we calculate the volume of an individual prism? Well, prisms in general are calculated by finding a representation for the base area, which we're going to use capital B, and then multiplying it by the height of the prism. So a prism is defined as some shape where the two bases run parallel to each other and are the same shape themselves. Okay, so what's going to be important in this method is that when we make our slices in a particular direction, the shape of the cross section is always the same at any slice along some interval. Okay, so super important idea, because if the slice is always the same shape, then we can use these prisms to make an approximation knowing what a prism is. So two bases of the same shape running parallel to each other. So if we take base area, multiply it by the height, we will get the volume for our prism. So looking at this particular example, imagine we're in a coordinate plane where we can see the height of our prism is going to be our delta x. And then we have to figure out a way to calculate the area of our cross section. And if we multiply it by delta x, we will be able to get the volume of that individual prism. Now, how we calculate the area of this cross section, we're going to cover later in the video. But to show you how this can be used in a more general idea, rather than specific examples that you might see in class, we're going to derive the volume formula for a sphere. And we're going to do that through that method of identifying the volume for a prism, adding them all up, and as we take the limit of the height of those prisms approaching 0, or as the number of prisms approaches infinity along the interval, we get an exact representation for the volume of that particular shape. So let's draw some sphere, and let's imagine we have some center point. And we know that ultimately we want to find a representation for the volume of some prism. Okay. Now the height of our prism, dx, is going to represent the height of our prisms, just like the dx represented the base of our rectangles in our integral for calculating two-dimensional area. So all we have to do is figure out a representation for the area of a cross-section when I ultimately write my integral, because I know the integration along some interval is the act of accumulating whatever we're integrating over that span. So I'm accumulating areas of prisms, and we're going to think of this dx as the height of our prism. So our integral, we're going to do area of the cross-section, which is going to be our base area, and then times dx. Okay, and we're going to integrate from one point to another, and we'll figure out. So let's look at the example of this sphere, say. So let's say we're at a point where we make a cross-section over in this area. And if we make a cross-sectional slice, we know the cross-sectional slice for a sphere is a circle. So if we can calculate the area formula for this circle, we'll be able to integrate that and ultimately get the volume. So where the slice was made, we're going to say that it is x units away from the center of the sphere. And the area for a circle is dependent on us being able to represent the radius of this circle, which is drawn or represented through this blue line. So how do I get the radius of this cross-sectional slice? Because if I can represent that, then we can come up with an area formula for any cross-section circle that is made or that is observed. So how we're going to do this is we're going to triangulate this by introducing a line from the center to this point here. And the reason we're going to do that is because that red line I have drawn represents the radius of the sphere, which we're going to call r. And through Pythagorean theorem, knowing that r is fixed, no matter where I make a cross-sectional slice, that length of the radius of the sphere does not change if I were to implement that. Now, x is going to vary distance from that center point in a horizontal direction, but I can now find a representation for this blue line through Pythagorean theorem. And that radius of the cross-section is going to equal the square root of the radius of the sphere squared minus the distance from the center squared. In fact, let me write that in blue to stay consistent so you know what that's referring to. So what we have here, the radius of any cross-section. So if I make a cross-sectional slice at any point, this is how we can represent the radius for that circle. Now, what also is important to note is that we should be making our cross-sectional slices perpendicular to some line. And the line in this case we're making the cross-sectional slice perpendicular to is that horizontal axis that runs through the center of the sphere. So whenever we make our cross-sectional slices, we want to make sure we're designating a line that we're making the slices perpendicular to. And the problems that you do see in class related to this idea it will tell you what direction to make your slices. So knowing that we need to integrate the area of our cross-section, and knowing that the cross-section is a circle, and knowing that the area of a circle is calculated or dependent on the radius, we can say pi as the area formula for a cross-sectional shape, in this case, the circle. So now let's incorporate this into our integral. Area formula, which is going to be pi. Now, because it's going to be a square root squared, we're just left with this, r squared minus x squared, dx. So again, area for the cross-section shape, height of the prism, you can think of it like that, but that dx is not going to be involved because that dx is approaching 0 as we incorporate more and more prisms to get the actual volume of the shape. Now the question is, what do we set our lower and upper limits of our integral equal to? Well, how are we integrating, or what are we integrating along? Well, we're going from this point to this point, right? So we're going along this horizontal axis because we're making our slices perpendicular to that, right? Just like if we're making our rectangles that run perpendicular to the x-axis, we're integrating with respect to x. But if we made our rectangles perpendicular to our y-axis, or I should say the heights of our rectangles are running perpendicular to the x in the first case, versus the height of our rectangles are running perpendicular to the y, we would integrate with respect to y, or that vertical axis. So our prisms, the radii of these base values, or sorry, the base shapes are running perpendicular to this horizontal axis. We're going to integrate along this horizontal line. Now, how far left are we moving? Well, the length of this and the length of this are radius values. But imagine this is our origin in the coordinate plane. So we're going from positive r direction, negative r direction here. So we're going to integrate from negative r to positive r. This should give us a volume for a sphere. So let's see what happens. Integrating what's inside. We can distribute that pi if we want. Or better yet, maybe a much cleaner solution was like, let's remove that constant value of pi and work with this. All right, so we know how to evaluate integrals. What we're going to do is take the antiderivative, but it's with respect to x, so we have to pay attention to that. So r squared we're going to think of as a constant. So the antiderivative is r squared x minus 1/3 x cubed, evaluated from negative r to r of pi. When I plug in negative r, we're going to get positive r to start. We're going to get r cubed minus 1/3 r cubed minus negative r cubed plus 1/3 r cubed. Now let's clean this up. So r cubed minus 1/3 r cubed is 2/3 r cubed. And then negative r cubed plus 1/3 r cubed is negative 2/3 r cubed, but then minus that becomes positive 2/3 r cubed, for a total of 4/3 r cubed. And what do we have here but none other than the volume formula for a sphere? And we derive that formula for some radius r using this idea of calculating volume from cross sections. So we identify how to represent the cross-sectional area, and we integrate that cross-sectional area along some interval, and that is how we're going to calculate volume using this method. Okay, so that is the idea that we want to hammer home. So let's summarize that by saying volume from cross sections will be calculated by integrating along some interval the area of your cross section dx. Okay, if we're going to integrate with respect to x. So a of x is equal to the area of a cross section. So that is the main takeaway. And now we can understand this integral, the area of our cross section, that dx, think of it as your height of your prism. So we're integrating or adding up volumes of prisms. Okay, that's what that integral is telling us. An infinite number of prisms to get an exact representation for the volume as the heights of our prisms approach 0. But main concept, integrate the area formula for a cross section. And it is super important that in order to use this, cross-sectional shapes, so I'll say slices, must produce the same shape. Okay, so when we make a slice in a specific direction running perpendicular to some axis, every single time the shape must be the same to use this method. Okay, that way we can come up with a general representation for the area of that particular shape. So let's take a look at what you might be faced with. So we might have some region, call this R, of space where we have to calculate the volume of some figure where the cross sections made, or the cross-sectional slices that are made in this region run perpendicular to, say, the x-axis or to the y-axis, and they're going to tell you what type of cross-sectional shape is a result of that. Okay? So here's what we want to be able to do. When I have a problem like this, I like to think of looking at this region of space from a bird's eye view. So imagine we have some three-dimensional figure. We're looking at it on a bird's eye view. So this region we can think of as the boundary of the shape. And let's say we're making slices perpendicular to the x-axis. So our slices could be anywhere in this region, but they're going to run perpendicular to the x-axis. Okay? We're going to be given what shape that cross-sectional slice is going to produce. So we have to figure out that once we know whatever shape we're dealing with, how do we represent the area of that shape for this specific region? Okay? That is going to be dependent on you calculating the length of these red slices that I'm making. So you always want to be able to find the length of a slice at any point. So can we represent the length of these slices, and then how do we know, or what does that slice represent on our specific shape? So first, let's cover out how do we find the length of the slice. Imagine our top function is f and our bottom function is g. The length of that slice, if it's made perpendicular to the x-axis, is going to be top function minus bottom function. If they tell us that the slices need to be made perpendicular to the y-axis, then we now have to reformat our functions in terms of y as opposed to defined in terms of x. So this function that's to the left, f of x, we would need to rewrite in the form of f of y and g of y. And to find the length of that line, we would do right minus left, or top minus bottom when we change our perspective. So depending on if you're going to integrate with respect to x versus y, just make sure you're paying attention to how the functions are formatted. We want them defined in terms of x or y, depending on the direction of the slice. And then we do top minus bottom function to find the distance between the function, which is the representation for the length of our slice. Now, once we've determined what the length of that slice is, we must be able to identify what that represents on our shape. So a common suggestion is to draw whatever cross-sectional shape you are working with. So let's start with, let's say, the cross-sectional shape we're told is a square. So keeping in mind that we know we need to integrate, and we'll call this point A and this point over here B, the area formula for our cross section, that's all we have to do to get our volume. How are we going to represent our area formula? Well, we know that if they tell us the base of our square sits in region R, and you're told to make slices perpendicular to the x-axis, then those vertical slices I have drawn in red are going to represent the base of your square. So imagine you're projecting out, so we're looking down on a bird's eye view, and we're projecting up towards us as we view this region of space. So this is the length of our letter, which we know is f of x minus g of x, the distance between the two curves. And if I want the area formula for this cross section, because ultimately that's what I want to integrate, we must do that side length squared, because we know that's how you find the area formula for a square. So this is the computation you would make if your cross section is a square. What if we're told that the cross-sectional shape is a circle where the diameter of the circle is what's represented by the distance between the two curves, and we want to make our slices perpendicular to the y-axis. So now we know that that blue line I have drawn, which represents just a arbitrary slice running perpendicular to the y-axis, that represents, say, the diameter of our cross-section. So I'm going to draw in that blue slice here that represents this. We know area formula is what we're after, because that's what we're going to try to integrate, and we know area is calculated by pi r squared. So the radius is only half the length of the diameter, and we know the diameter is equal to the length of that blue line. How do we calculate the length of that blue line? Well, it's the distance between the two curves. But remember, we're integrating with respect to y, so we want our functions defined in terms of y. So if I divide this whole thing by 2, I'll be able to get our radius. And then if we integrate from a to, we'll have to figure out what this top value is. Let's call that point C. We'll integrate from a to c of pi, the representation for the radius, squared dy if we're going to integrate with respect to y. So that's what you would have to do for your circle. And if it happened to be a semicircle, which sometimes pops up, well, instead of pi r squared, we're going to do 1/2 pi r squared, and we just have to add that constant 1/2 into our integral. Another shape you might come across is a triangle. Specifically, equilateral we'll look at. So let's say the base of our equilateral triangle sits in region R, and we're making slices perpendicular to the x. So we're going to say that this piece down here is represented by f of x minus g of x, right? The distance between those two curves. And we know the area formula for a triangle is 1/2 base times height. We have the base. We need to be able to calculate this height. To do that, we're going to have to do a little work off to the side. So what happens when we calculate this height is we generate a 30, 60, 90 triangle, knowing that if it's equilateral, which is a key piece of information, all the angles are 60 degrees. So when I make that slice perpendicular to the base, we cut it into a 30, 60, 90. And we know that this hypotenuse side, or it's actually better to use this side. So I'll show you the relationship for the 30, 60, 90 actually. So this is a root 3, and then 2a. So what that means is if we can get that side opposite the 30 degrees, we can get a representation for that. If we just multiply it by the square root of 3, we'll be able to get the height of our triangle. And in fact, if we scale all of these down by 2, or divide them all by 2, we'll see another representation for a 30, 60, 90. So how do we get the side opposite 30? Well, we're just going to take that expression that represents the base, and we're going to divide it by 2, and then we're going to multiply it by the square root of 3 to get my height. So in conclusion, if you have the base, you know that the height is going to be square root of 3 over 2 times the base. And that is derived through the idea of 30, 60, 90s. So that's kind of a neat thing to pay attention to, which we can even clean this up into square root of 3 over 4b squared. That's the thing we're going to integrate. So those are often the most tricky, because sometimes it's difficult to remember the relationship for a 30, 60, 90. But if you do forget, you know all the sides are the same on an equilateral. You cut this, you know this is x over 2, and you can do Pythagorean theorem with this and this to figure out what this side relationship should be. But through doing enough of these, you can see that you're going to integrate from a to b. 1/2 the base is f of x minus g of x times the height, which is square root of 3 over 2 f of x minus g of x dx. Right? And we can condense that down if we want, because ultimately we're going to have to anti-differentiate this if it's a non-calculator problem into square root of 3 over 4 f of x minus g of x squared dx. And you could pull out that square root of 3 over 4 outside the integral and work from there. So that one's a little more complicated, as you can see, but still doable if you understand the relationship between sides for equilaterals. So those are just some examples of cross-sectional shapes that you might come across. But the key thing, and we'll summarize here, to do is in these types of problems, you want to be able to do the following. Identify the direction of the slice, which is often given to you. So do they run perpendicular to x or perpendicular to y? That's going to dictate whether or not you're going to integrate with respect to x or with respect to y. So if they're running perpendicular to x, you're integrating with respect to x, and if they run perpendicular to y, you're integrating with respect to y. So you're going to may have to reformat your functions for the latter. Now, once you've determined the direction of the slice, you want to be able to calculate a representation for the length of those slices in that region at any point. The length of the slice is often the distance between two curves. If I were to remove g of x, and I just had the f of x function, we were looking at a region bounded between f of x and the x-axis, well then the distance between the function and the x-axis is just the function output for f, which is often nice, because then there's less calculations to be made. But if the region is bounded between two function curves, we know that to find the length of the distance between the function curves is always top minus bottom. So find the length of each slice. And then you want to determine what does that slice represent on your cross-sectional shape. And the reason that's important is because we know the length of that cross-sectional slice is going to be incorporated somehow in our area calculation for that cross-section, right? So once we know what it represents, then you want to be able to format the area formula for the cross-section in terms of the functions given. So common shapes you're going to have to deal with. Squares, which is just side squared. Rectangles, base times height. Triangles, 1/2 base times height. Or circles, pi r squared, or semicircles, 1/2 pi r squared. So be on the lookout for those types of area formulas, those structures. And then once you have a representation for the area, you are now ready to integrate the area formula for that cross-section along the given interval. And once you do that, you will have calculated the volume of this figure utilizing cross-sections.